Thank you so much for coming this special workshop series, Practical Optics Workshop. This is the invited lecture, and I'm so happy we are here today because, in my opinion, at the university, we do care research, development, new discoveries, but at the same time, unless we share and use it to educate next generations, we are not doing the right thing at the university. Today's lecture is very special for that reason, because this is not really about like new discoveries or recent researches, but more about laying out the roadmap, how you educate and teach the next generations. So it's my great pleasure to have this practical optics workshop today. Once again, thank you so much for coming. Just one note, we are going to record this because this kind of talk must be recorded, and we will continuously use it for many future uses. What that means, although you may have exciting questions as the talk goes, please wait until the talk ends. And then at the end of the presentation, we'll have a Q&A session, and we can have a great discussion about the educations and about few slides he presented, all that kind of things. Without further ado, I want to introduce not the speaker, but the one who is going to introduce the speaker. It's my great honor. So Jim, please come and introduce today's speaker.
I have one. Okay, well, thank you very much. So we're very honored today to have Virendra Mahajan as our speaker. Now, Vinny is actually one of our products. He got his PhD here in 1974. And then he went to Draper Lab in Cambridge, Massachusetts, and worked there for 9 years. And then he after that, he moved to the Aerospace Corporation in Los Angeles, and he worked there, for approximately 30 years. So during all this time, Vinny was doing classified work. So I don't know what he was really doing, but he actually, normally if you do classified work, you can't publish papers. Vinny published almost 70 papers and 5 books. Can you believe it? 5 books. I brought 2 of them here. I would have brought all 5, but they're too heavy to carry. So 5 books. Amazing. He gave many talks and short courses around the world. In fact, he's still doing that, going all around the world giving these courses. He's a fellow of OSA, fellow of SPIE, and a fellow of the Optical Society of India. He won the 2006 SPIE Conradi Award and a 2015 SPIE Educator Award. Now, as I said, Vinny has given a lot of talks and lots of courses, and about 2004, I think it was, I thought, we really needed to have a course here in optical imaging and aberrations. So I approached Vinny, can you help us? And Vinny said yes, he'd be glad to teach a course. Now, he was working for Aerospace in Los Angeles, so I thought he would probably, do this remotely from Los Angeles. But not Vinny, he doesn't half do something, he really does it. So he would get up early in the morning, get on a plane, fly to Tucson, teach all day, and then fly home at night. Furthermore, he got his company, Aerospace Corporation, to pay for all the travel expenses. And then he said he didn't even want to be paid for giving the courses. So you can imagine how happy I was. So he did this for 9 or 10 years he did this. I mean, just incredible dedication to optics and to the College of Optical Sciences. So for that, we thank you very much. Now, we wanted to do something to thank him for this. So we named a laboratory after him. And this is, as you can see, their room 436 or 430A, whichever number you like to use. And I never quite understood why there's two numbers on that.
Buy one, get one.
Yeah. But the Mahajan Applied Optics Laboratory. Now, I don't know if you've been down there recently, Vinny, but I just went down there and looked today. Just to the right-hand side of that is a picture of Einstein. And the left-hand side of the door is a picture of Thomas Edison. So, did a good job decorating it. So anyway, you know, we really have a lot to thank Vinny for. So thank you very much. And again, thank you for what you're going to do now. You're going to give us a talk on the roadmap for teaching optical imaging and aberrations. Vinny Mahajan.
Thank you very much. I appreciate the introduction. I'm glad to be here. I spent 3 years here from 1971 to 74, not in this room, but on the floor above in what now is perhaps the oldest building among the few optical sciences buildings. And every time it's a joy for me to come here, and this time it's no exception. I guess one of the major things that has happened is the name of the college has changed, the name of the Optical Sciences Center has changed, and for good reasons. And I admire what Jim has done for the school and establishing all those scholarships and endowments. But I'm here to talk about optical imaging and aberrations, how I think should be taught, because that is how I have done it myself. So it is based on my own experience, and happens to be that this is a talk I gave this year in May at a conference in Quebec City in Canada, city I had not been to, and I wanted to go there. That's why I gave the talk there. There was a conference there called ETOP, Education and Training in Optics and Photonics. And it seemed like an appropriate talk to give there because educators from the globe had come there. And the room was indeed full of professors and junior professors and the like. So that's what I'm going to do. And feel free to ask me questions at the end. What happened to page down? This is my purpose, to show you how I think optical imaging and aberrations, and my focus is on aberrations, because that is what is generally left out, more or less. And I want to emphasize that instructors should focus more on the concepts with homework. And this is often done in the US, but in other countries it is often skipped as well. I have an experience. I was at a university in Ireland, and I gave lectures there for 5 days in a row, 3 hours every day. And then they asked me if I would like to come back for a year and teach and so on. And I said, fine. And I was skeptical about the homework there. And I said, I have to assign homework, and the attendees have to do the homework. And in Europe, in some countries, they don't assign homework, and the students don't want to do the homework. And that's why they don't learn, to my way of thinking. And so I never went there thereafter, because I'm there, yes, to teach, but make sure they learn as well. And I honestly and sincerely believe if you don't do the homework, you really do not learn. And my personal experience in my education in India was similar. We didn't want to do the homework. We thought, we are now senior students, so we are not in high school anymore, and therefore we didn't do the homework. Homework was not assigned very much either. As a result, I must admit I didn't learn very much. So anyway, that's my objective here, to illustrate what kind of homework should you really give. Make it interesting and relevant so that students want to do the homework. These are the obvious two topics that you deal with when it comes to optical imaging. And aberrations kind of stand between the two. And when we come to that, I'll talk about. In ray geometrical optics, you start with Gaussian imaging. And I'll quickly illustrate by figures simple things that normally instructors would in fact go through and students would learn. If you are learning geometrical optics in a department of physics or somewhere, they will end up with Gaussian imaging, the first topic, and not get to paraxial ray tracing. Why do they have to learn paraxial ray tracing? If you don't learn things like what are the element sizes. You can calculate the image of an object given the characteristics of the system, but how do you know how big the lens should be and why so? Why different elements should be or what sizes would they have and so on. And certainly you want to know how bright is the image. Well, if you want to know how bright is the image, you have to know about the aperture stop. And the moment you talk about the aperture stop, you will end up talking about the entrance and exit pupils. And if you have a 2-mirror telescope, and if it is radially actually symmetric, it'll be having a certain amount of obscuration. Well, how do you calculate the obscuration unless somebody tells you what the sizes of the mirrors are? So you have to know the sizes of the mirrors and then thereby know what the obscuration is. And I lay here that I will talk a little bit about aberrations. I cannot talk too much because that obviously is a course in itself. So Gaussian imaging. The first thing you want to settle is the sign convention. The archaic sign convention is some of the, perhaps most of the old books, depending on is the object real or virtual, is it on the left side or the right side, etc., is not very practical at all. For one element you could do it, 2 elements maybe. As soon as you have more than 2, you run into confusion, right of what, left of what, and so on. So use the Cartesian sign convention. And of course, students who are now taking the optics course, they have learned what Cartesian sign convention is. And you do want to use the Cartesian sign convention also because if you are going to move further beyond this kind of a class, the optical software that you can buy and use and learn from to do anything also use the Cartesian sign convention. So that's important. And I will kind of illustrate that by way of figures. Notice I have the distance, object distance S, image distance S prime, for example, and I have put parenthetical minus sign. That means that quantity S is negative, numerically negative. So if the distance of the object in this figure happens to be, say, 10 centimeter, in your equation you are going to substitute S equal to minus 10. And similarly for the angles. Distances are perhaps easier to handle, angles are a little bit harder too. But as long as you stick to the Cartesian sign convention, it should be okay. And using the so-called paraxial approximation, which is what Gaussian optics is about, I give you the equation for imaging, and you immediately, quickly can tell what is the focal length. And there are two focal lengths, object side focal length, image side focal length. One of them may be positive, the other may be negative, and there is a relationship between the two, as indicated here, depending on the values of the refractive indices. In my mind, graphical imaging is very important. Most double E students who learn this kind of stuff, they want to deal with 2 by 2 matrices, which you can, and the computer software does use those matrices. My feeling is, yes, if you really know how to use those matrices, maybe it's okay, but you really don't know which way the light was coming, where it was going, and was it going in the right direction or not. Those matrices don't tell you that. And therefore, this kind of graphical imaging, where you just have to trace two rays, very simple. Once you know the focal points, you draw a parallel ray, it goes through the image side focal point. You draw a ray going through the object side focal point, it comes out as parallel. The two rays intersect, and that determines the image point. Now, two rays will intersect somewhere unless they were diverging, in which case you will get a virtual image. But it may or may not be the right point unless you have done it right. So you draw a third ray. And third ray in this simple example of a single refracting surface is the ray that goes through the center of curvature of the surface. And that ray is straight, it goes through without being undeviated. Why? Well, angle of incidence is 0, therefore angle of refraction is 0. Three rays, if they meet on the drawing you are making, your solution is presumably correct. If they don't, you have to look for a mistake somewhere that you may have made. Homework problem. Homework problem, as I recall from my youth, hemispherical surface. It used to be a paperweight, and it would have a flower embedded in it. And in fact, I'm sure at a gift shop you could perhaps buy these things. I wanted to bring one with me just to show you. But the flower is at the middle of this hemisphere, and you try to calculate this image. It may seem like a trivial problem, and perhaps it is, but until you do it, you find out, it makes you think, oh, where are those three rays that I wanted to find make sure my image is located correctly. So, to show the transverse magnification, consider a cube as an object. What does the image look like? Why, it doesn't look like a cube. And it will be interesting to draw it for the student. Of course, the instructor has to construct a reasonable problem, and it's a truncated pyramid that the image comes out to be. Isn't that interesting? You could give problems, okay, here is the object, find where the image is, and so on. That's just arithmetic, as long as, of course, you are putting in the right signs and so on. But make the problem interesting. Imaging by a thin lens consists of two surfaces. You find the image formed by the first surface, then image formed by the second surface, and you get the imaging equation as shown here. And imaging by a thin lens is perhaps the most famous example of imaging that we as students would go through, and perhaps in our later life also. But we did it for a thin lens. In the title it says the word thin. What does that mean? We just go through the equation, forget about the fact that a lens, to be fabricated, it has to have some thickness. Ask the question, is that thickness small enough that you can treat it as a thin lens? And if it isn't, well, now you have to figure out what equation should I use because my lens turns out to be not so thin. And we'll talk about that in a few moments. Similarly, graphical imaging by a thin lens. Well, two rays are standard through the focus, either on one side or the other. What is the third one? Well, it's a thin lens, practically zero thickness. The ray that goes through the center of that lens goes undeviated. Very easy to draw. Find the point of intersection of those three rays. If they meet at a point, well and good. You have presumably the right answer. Homework problems. And in the beginning, I emphasized homework is absolutely necessary. Now, I have talked about imaging by thin lens. Students seem to understand it and so on. But what's happening as you calculate the image? You change the object position, the image position changes. Is that what happens in practice all the time? The answer is no. I have a camera here. Image position is fixed, no matter where the object is. How is that accomplished? My eye forms the image. Object could be in any of these rows, even at infinity. But the image is formed on the retina. A retina is fixed. How is that accomplished? Well, eye has an accommodation. The lens in the eye, inside the eye, is flexible. It's changing the focal length instantaneously. You know, I look near, I look far. Of course, I wear glasses in addition to. And therefore, problems should be formulated and students should be quizzed to think how the image position is fixed even though the object position is changing. And I'm sure if you raise this kind of a question, students will become curious. Hey, I need to learn this thing. This is interesting. Use of spectacles, near and far-sightedness, and lot of us wear glasses, perhaps not think if I am nearsighted, is my lens positive or negative? We don't think. And if I am far-sighted, what happens then? And we should show it by diagram. Where is the image being formed unless I wear my glasses? I know the image is blurry. Is it beyond the retina or is it in front of the retina? And by formulating a simple problem, you make the students think. I'll come back to this accommodation and the like. As I say at the bottom, it's the perfect example of adaptive optics, where the eye is adapting instantaneously to the distance as it changes. Now, adaptive optics, as we know, we immediately think of a deformable mirror and the like, but so is the eye. And I think students should be exposed to this feature in these kinds of words to make them think. Imaging by a general system, you know, you find the principal planes and distances are measured from those principal planes and the like. The problem reduces to, if you are given a system with whatever characteristics of its elements, the problem reduces to finding the principal planes. Once you find the principal planes, the equation as given here is identically the same as that for a single refracting surface. What has changed is the object and image distances that were being measured from the vertex of the refracting surface, now they are being measured from the principal planes. And this point should be made so that there is kind of a continuity as the instructor progresses and the students progress. Imaging by a mirror. Imaging by a mirror, I show here in small letters that instructors will tell you n equals 1 and n prime equal to minus 1, and you can therefore get the equations from the equations you just derived. And that is well and good. Instructor can save time by so doing. However, students must go through the same procedure that you did for a single refracting surface. Otherwise, it does not sink in. Otherwise, it becomes kind of mathematical only, that imaging, how it works for a mirror, especially when you are going to do a 2-mirror telescope. Here is a practical example. Looking into the eye of another person. And a poetic version of it is, I have said it a little differently here. You look into the eye of your lover and say, see what you see in my eye. Who do you see? She sees, or he sees, her or his own picture. Why? The reason is the cornea is slightly reflective. It's a convex mirror, forms the image of the person looking into your eye, and that person sees him or herself. And maybe you haven't paid attention, but try it. And obviously you see how big the image is. And you should be able to figure out, for that size of the image, what must be the curvature of the cornea. And it's roughly the same for all of us. You should be able to find the size of the image, why the image is erect. Of course it has to be erect, otherwise, boy, life would be rough if you saw your own image upside down. Okay. Here is another interesting problem. Most of the cars, not so much nowadays, because we have the sonar signals to tell us if there is a car on my right side and I'm trying to change the lane. And these mirrors are mounted on the passenger's side typically, and this kind of imaging takes place, I understand, in some European cars on both sides, that it gives you that signal. And it says objects in mirror are closer than they appear. But it's really not the object that is appearing, it's the image of that car that you are looking at while you are driving. And of course, once you learn paraxial ray tracing and so on, you could start talking about the field of view. You know, how far can the car be so that you can still see that in your mirror properly, and so on. So when I say make the problems interesting and relevant, think of such matters rather than just giving plug-in problems that reduces to arithmetic. This is what I just talked about. Show it on the chart, and of course the image is erect, and that should give an idea that we think that passenger side mirror, for that matter, other mirror also on the driver's side, is flat, because we can't feel it. Is it really flat? But it's not. It is curved, and you can measure, in fact, the curvature if you want to. And I'm not very good at doing these things, so I called my friend Bill Swanner, and he measured it for me. He gave me a number, and I estimated. Yeah, he measured it correctly. Now, paraxial ray tracing. This is often, I would assume, is missed, at least in EE classes, EE schools, that is. Similarly, physics schools where they would teach this kind of a subject, and they wouldn't go through this. But in my mind, it's very important, because otherwise you don't know how big the elements need to be. And certainly, don't imagine that you can make it as big as you want. The bigger you make, the more expensive it becomes. And if you don't, it doesn't have to be any bigger than a certain number, well, that's what you want to do. Make it as small as possible. How do you determine the field of view of a system? Oh, by tracing rays. And I'm saying tracing rays on paper and pencil. Use the paper to draw more or less by hand. Otherwise, you can take, graph paper as we used to. On the computer, you could these days, of course, do the same. And in my mind, paraxial ray tracing must be an integral part of a class on geometrical optics. And I'll just go quickly over a few charts. Refracting surface, I just did that a few minutes ago, and now I'm going to do it by tracing rays. And I have a ray at a certain height, x0, incident on the surface, it's reflected, refracted, I should say, and go through very few simple steps, and you can immediately derive these relationships that are recursive. X1 in terms of x0, angle beta 1 in terms of beta 0, and therefore x2, x3, and similarly the angles. Well, we skipped doing the problem of a thick lens. Now that we know how to trace rays paraxially on paper using pencil, I do it for two surfaces. And by so doing, I get the equation for the focal length of the thick lens. There are two pieces to it. The first piece is for a thin lens. The second piece has the thickness T of the lens. And as before, we want to calculate the focal length. Focal length is x3 equal to 0, where the ray intersects, parallel ray intersecting the optical axis. So x3 equal to 0 is the condition. Determine what the focal length would be. Focal length from where? Now we have two surfaces. You have to determine the principal point. So it becomes, in a way, interesting. Oh, okay, I have to learn about the principal points, and thereby determine the effect of the thickness on the focal length. And for a thin lens, you go through the steps. Image by the first surface becomes the object for the second surface, etc. You could easily give the homework problem. Here is a thin lens. We are calling it thin. Let's assume it is thin. What is its focal length in water? It's the same problem, except the surrounding medium is not air, therefore it's not 1. It has some value other than 1. Calculate the focal length. And before you even calculate the focal length, you could easily ask the students, hey, is the focal length going to be longer or shorter? Okay, start thinking. And If it is longer, why? If it is shorter, why? You could have a very good discussion about. Or just tell the students when you do the homework, before you derive it, answer this question honestly. And then derive the equation, figure out if it is longer or shorter. Refractive index of water is 1.33, if I remember correctly. You should know by how much, longer or shorter. 2-mirror telescope, trace the rays. Parallel ray, incident on the primary mirror, goes on to the secondary. Now you know the height of the secondary. Where does it touch the secondary mirror? Primary mirror you assumed unit length or whatever you want to choose it to be. Now you know the size of the secondary mirror. Until you did that, you really didn't know. In your imagination, of course, you had, well, that mirror has to be smaller, otherwise it won't let any light through. So you know the size of the secondary mirror, and if the image is formed beyond the primary mirror, there has to be a hole in the primary mirror. How big a hole? And immediately you start thinking, my God, if I make the secondary mirror too big, light won't go through or not much. I need a hole in the primary mirror. If I make that hole too big, well, I'm losing light again. Students naturally start thinking about bending of the rays. And of course you want to know what the obscuration ratio is, and I typically have given the homework problem of the Hubble Space Telescope, just so that they have some contact with reality. I tell them 2.4 meters, 2.4 meters is its primary mirror diameter, figure out the secondary size. And if you want to go a step further, figure out the secondary size for a field of view of some number, 1 degree, 5 degrees, and so on. Calculate the size of the hole required, and so on. And that's about the obscuration ratio using those paraxial rays. And you can see the focal point F is when the ray comes out of the system and intersects the optical axis. And if you push that ray backwards, where it intersects the incident ray, that's the principal plane. And you can easily ask again about the Hubble telescope, just to make it fixed on something real, as to how much its focal length is. Okay. Field of view. Trace a ray at some angle, choose an angle, and see what happens to that ray. Does it even come out of the system? And of course, you are making the secondary mirror bigger and bigger as you go to a larger and larger angle. And immediately you start thinking, oh, it can't really have a very large field of view. But you could ask the question, give me a limiting field of view where a ray at a certain angle stops coming out of the system. As an example, you make a criterion, and the students have to go through determining whatever you have asked to find out. Now, you do want to tell the students life does not survive only on paraxial optics. If you are doing something real, you have to go through, use the software, computer software, to get real results. But you already have approximate results having done the paraxial problem. Image brightness, I mentioned, you want to know how bright the image is. Don't just leave it with the size of the image and its location. Figure out how bright is it. And that depends on how much light gets through. Gets through where? Is it the first element it sees? No. You have to determine where the aperture stop of the system is. And once you know that, entrance pupil will tell you how much light is getting through, exit pupil will tell you how much is getting out, and you need to know the entrance and exit pupil for doing the whole problem. So I'll just illustrate. I have two lenses, and the problem gets cumbersome very quickly. I have the aperture stop between the two systems, and typically we say initially light travels from left to right. Well, my object is on the right side of the first lens, so I have to think, how am I going to calculate its image, which would be the entrance pupil. And of course, for the exit pupil, it's in the right position that normally we would be trained to calculate the image. We naturally think, oh, I got circular mirrors, so I must have circular aperture stop, circular entrance and exit pupils. But as you go off axis more and more, the pupil becomes non-circular, and I just illustrate. It looks more kind of elliptical. And if that is the case in the system you are going to be working with, you have to deal with it, that it is elliptical. The point spread function is going to be for an elliptical aperture, no longer circular, and so on. So that's kind of useful awakening to make sure the students don't just think automatically it's circular and nothing else. Now, I'm kind of done with Gaussian imaging, and I started with a spherical surface. And of course, when we draw a lens, we draw two spherical surfaces, even if not exactly by hand when we draw, but in our mind it is that they are spherical surfaces. What if the surface is not spherical? What happens to Gaussian optics? What's the image location? Now, is it any different? The answer is, as long as the vertex radius of curvature of this non-spherical surface is the same as that of the spherical surface that I was dealing with a moment ago, Gaussian imaging doesn't change. Okay, well and good. What does change? Why do we use non-spherical surfaces? That's where the aberrations come in. Spherical surface does not give a very good image. So we try using parabolic, paraboloidal surfaces and the like. And of course, these days, people are talking about free-form surfaces, taking liberty with the shape of a surface. It's hard to make, perhaps hard to test. That's for somebody else to worry. But as an analytical person, I'll take liberty and design whatever surface shape that will give me a good quality image. Of course, at some point, if not you, your associate would have to worry about making it and testing it. But students must know that it's not always spherical surfaces, and in fact, rarely are they. Now, beyond Gaussian imaging. Gaussian imaging at most, at best, gives me the image size, image location, image brightness. But as far as the image quality is concerned, it doesn't deal with. By virtue of Gaussian imaging, image is perfect. When we calculate the image, we don't think of its quality. But even more important, we learn Gaussian imaging by way of paraxial optics, paraxial rays. The angles are small. But when we calculate the image formed by a lens or a lens system, do we ever think, oh, this object is too big, paraxial rays won't apply to it, Gaussian imaging doesn't apply to it? We never ask ourselves. We just calculate the image. Only if you ask the question about the quality of the image, now you have to think beyond what you had just learned. In particular, I say my object distance 10 centimeter. But my object is big. If I consider a point object off axis at a reasonably large distance, well, angles are not paraxial. Angles are large. So even the image I just calculated, where it's located, what its size is, I inherently assumed my object was plane, my image is planar also. But that point object was maybe at 15 centimeters, depending on the size, the diagonal distance. But we never use diagonal distance. We just, okay, how far is the object? What does the diagonal distance being so different from the axial distance do? That means a good quality, even Gaussian image, is really not located in that plane that we just thought it was. And that introduces what is called the Petzval curvature of the image. I mean, I remember from my student days, people who knew about what Petzval curvature was, and I would say, these guys are, I don't know what they are talking. But it's obviously that the image of an extended object is actually formed on a spherical surface if you want a relatively good quality image. And I'm not talking about other aberrations at the moment yet. So that's what Petzval curvature is about, and students at least should be reminded that all our equations were based on paraxial rays. We didn't pay attention to how big the object was, and it gives the image on a spherical surface. And lens designers work very hard to balance the Petzval curvature of one element against another to make the Petzval curvature as little as possible so that you can make the observation on a flat surface. You know, you are not going to make chips that are not flat. They'll be very expensive. Some of our earlier surveillance satellites did have focal surfaces that were curved, but not anymore. Not anymore. Okay. So anyway, I'm going to switch to diffraction, and this I can go a little bit more quickly because most of you probably know quite a bit about. The first portion I'm sure you knew about, but there were things I wanted to remind you about. Aberration-free image, we start with point source at P, a perfect image at P prime. The rays, light goes through, a spherical wave is incident on the system, comes out a perfect spherical wave with its center of curvature at the Gaussian image point. Image is perfect. It's a point based on geometrical optics. But in reality, we don't get a point image. We get the Airy pattern, so-called. And if in fact the wave coming out of the system is not perfectly spherical, what happens? That's what we call optical aberrations. Deviations of the surface coming out of the exit pupil, differing from a spherical form. Those deviations are what we call wave aberrations. And if you trace rays, rays don't go through the Gaussian image point. They have a ray distribution, so-called the spot diagram. But you can imagine, and you want your students to imagine, oh, we have to learn about the aberrations, and aberrations can only degrade the image. They cannot, generally speaking, they cannot make things better. And so, here are the aberrations. And talk only about primary aberrations, so that there is some association with what they may have heard: distortion, field curvature, astigmatism, coma, spherical. And here, in my experience, I ask students in the audience, I focus on those who are wearing glasses, and I say, you're wearing your glasses. Have you ever looked at your prescription? I have never gotten an answer. Yes, sir, I have. Okay, if I get an answer yes, I would say, well, what does it say? Now, Professor Devuk did tell me that he has. It should say you have a focus error, you have perhaps spherical aberration, and if you have astigmatism, probably your doctor has told you, oh, you have astigmatism also. It used to be some years back, it would cost you more for the optician to introduce astigmatism also, because it's not radially symmetric. And believe me, I have given this kind of a talk, not this very talk, at lots of schools, different schools across the globe. And I never get an answer from people who wear glasses that they have ever paid attention to the prescription that they just received. They just go to the optician and say, make me my glasses. Calculation of wave aberration. This is a little stuffy to do, but for simple systems, you can on paper derive the primary aberrations: single surface, thin lens, mirror, two mirrors. And I think that's about enough, because it is not trivial. Nevertheless, if you don't go through some of it in some form, I say at the bottom that you are really depriving the students to appreciate the beauty associated with optical aberrations. Wave diffraction imaging. I'll talk about these things a little bit quickly. Airy pattern, perfect image, spherical wave coming out of the exit pupil. And you know the airy disk, radius 1.22 lambda f, f being the focal ratio, 83.8% of the light contained in the airy disk. And I asked the students the question, why the brightest point is at the center? Well, it's the focal point. That's the answer you would get. Well, I tell them, this is where the Huygens secondary wavelets are in phase. They interfere in phase. They interfere constructively. That's why it is the brightest point. Anywhere else, it will be less than the brightness at the center. Because from the center, spherical wave, the secondary wavelets originating on that spherical surface are equidistant, and therefore it's the brightest point. Once you tell that, immediately you realize, oh, if that wavefront was not spherical, it is wrinkled, it has deviations from a spherical surface, you know those secondary wavelets are not in phase with respect to that point. And therefore, the aberrations can only reduce the value at the center. And the value at the center is what we call Strell ratio. And before I talk about Strell ratio, I thought for entertainment I should show you for various aberrations what kind of patterns do you get instead of the Airy pattern. Strell ratio. Simply put, what is the value at the center if there is some aberration? You calculate its variance, sigma square, and if you convert it to phase variance, the expression is very simple. The Strell ratio, value at the center with aberration relative to that without aberration, meaning perfect spherical wave, that ratio is given by e to the minus sigma square. That's easy to remember. Don't put in 2 pi over lambda and so on and so forth. Just make it simple. Write it in terms of the phase aberration variance. And you know how to calculate the variance given the aberration data. And in your class, and don't keep in mind thinking, well, optical design class will teach them something about tolerances. Well, you know how to calculate the Strell ratio. Quarter wave of spherical aberration. Calculate what the Strell ratio would be. It's 0.8. By the way, Rayleigh is the one who first calculated that. He calculated the Strell ratio. At that time, the term Strell ratio was not around, although Rayleigh did his paper many years after Strell wrote. He calculated it for quarter wave, half wave, 3/4, 1 wave. He calculated these numbers to the 4th decimal place. Correctly to the 4th decimal place, of course. I still don't know how to calculate except with my hand calculator, or I go to somebody, can you calculate what the Strell ratio is for this kind of aberration? Here I have a 3-mirror system, and for simplicity, I say to the students, assume they all have some fabrication error. I want the Strell ratio to be 0.8. Tell me how accurately the optician has to polish those mirror surfaces. And I tell them the primary mirror of the Hubble telescope took 5 years to polish. And people wonder why it takes that long. It takes long because in this example, for example, I say lambda over 48 is the fabrication tolerance on each of those 3 mirrors if you want a Strell ratio of 0.8. And if lambda is visible light, that's a pretty small number. The key thing I teach is these are random errors. You add the variances of the surfaces and then take the square root. And don't forget the factor of 2. These are mirrors. Light is reflected, so any bump is doubled in size. Those 2 things I let them try to independently think about, and they often miss something about. Diffraction image. For incoherent object, we learn that the extended image is the convolution of 2 things. Convolution of the Gaussian image with the point spread function. We have learned by now what the point spread function is. So you Fourier transform, you get the OTF, PSF transforms to OTF. So students learn that OTF is the Fourier transform of the PSF. Well and good. They probably also learn OTF is also the autocorrelation of the pupil function. Pupil function, complex amplitude at the exit pupil. If you think only in terms of the Fourier transform of the PSF, you don't realize there is a cutoff frequency. But the moment you think of the autocorrelation, two pupils walking across each other, overlap becomes 0, there has to be a cutoff frequency. Now, OTF is a complex function. It has real and imaginary parts. What does it physically really mean? Mathematically, I know it is the Fourier transform of the PSF. I illustrate it this way. You start with a sinusoidal object, calculate the Gaussian image, which is exactly the same as the object, except for magnification. Spatial frequency will be different. For the image, write the complex OTF and write down now the diffraction image. The moment you write the diffraction image, you will find the contrast M is multiplied by the modulus of the OTF, and the phase has changed by the PTF, phase transfer function of the OTF. And of course, those two functions are frequency dependent. That's the only way I know that you understand the physical meaning of what the optical transfer function is. Otherwise, for an average student, it's just the Fourier transform of the PSF. This diagram I show just to illustrate what I just said. OTF typically, you know the function, but at least one OTF they should actually calculate. Here I give the example of the defocused OTF, and there are regions where the OTF is negative. What does that mean? That is what translates to contrast reversal. Bright portions of the object become dark, dark portions become bright. 2-point resolution. We all teach Rayleigh criterion, principal maximum of one falling on the 0 of the other. Okay, so good. And I can give these equations. I can calculate what the image looks like, and you can see, yeah, it looks interesting. And we talk about the dip in the middle, and that the dip is at 0.73. But so what? Do I really know now what resolution is? So here is the problem I ask. You're driving on the freeway at night, and there is a vehicle coming from the other side. And if it's far away, you don't know if it's a motorcycle or an automobile. What's the difference between the two? Automobile has 2-point sources. Simple question, at what distance can I tell if it's a motorcycle or an automobile? You know the diameter of the pupil of the eye, calculate the diffraction limited resolution for simplicity, and determine the distance at which you can in fact resolve the two headlights on the automobile. And in my simple example, I find it's 10 kilometers. And if I am giving this talk, say in the US, I have to tell it in miles. Well, I say it's about 6 miles. And you visualize, oh, about 6 miles, yeah, that's good distance, because otherwise, if it's a narrow road, I could run into, not knowing or thinking it's a motorcycle instead of an automobile. And of course, this is a very approximate resolution. Pupil of the eye, its diameter changes depending on the brightness that I am receiving from the vehicle on the other side, etc. But it gives you some idea of, and the distance comes out to be a reasonable number. And I showed you the aberrated PSFs for astigmatism, spherical aberration, etc. But for a random aberration, what happens? Where there is a mixture of these aberrations. Well, the PSF breaks up into these small, what we call speckles. That's the airy pattern in the presence of atmospheric turbulence. And what is special here is each bright spot is based on the actual size of the observing telescope, and the little ones, because they depend on what is the size of the overall image, especially if you take a long exposure, that depends on the coherence length of atmospheric turbulence, something we donate, use the notation R0. R0 is typically small, and therefore we do not get the resolution of the big telescope that we happen to have. Now, don't start thinking about the Keck telescope, which has adaptive optics and all, but there is a 5-meter telescope on Mount Palomar near San Diego, 5 meters, made long ago. If the resolution is going to be that of a telescope 1 centimeter, say, in size, why did we build 5-meter size telescope, I ask? And the answer is, so we could see dim things, even though not resolve them well, just to collect more light. And of course, there has been always a kind of discussion among people, astronomers, why did we go in space, the Hubble Space Telescope? Because on ground the resolution was poor, let's do it in space, we did. And then came up adaptive optics, and therefore we can overcome to a large extent the effects of turbulence. Now, Keck telescope is 10 meters in size. In fact, there are 2 of them, and I like to mention the first demonstration of real-time wavefront correction was done by our illustrious James Wyant at ITEC. He developed the real-time wavefront sensor called lateral shearing interferometer, and other people developed the little deformable mirror and gave a closed-loop demonstration. And I might add, my PhD dissertation, I'm sorry, there is somebody at the door at my home. But I used acousto-optic Bragg cells. Each cell will correct the wavefront error of the portion of the beam that is across it, and so on. And I demonstrated that you could control the phase by controlling the phase of the acoustic cell that drives it. But I know when I finished my degree and got my job, got my security clearance, and I found out deformable mirrors were real, developed by the Air Force, funded by DARPA. And of course, astronomers are the real beneficiary of this development of deformable mirrors. Military expenses are high. Program I worked on, missile warning satellite, we were spending close to $1 billion a year, and went on for many years. I could tell you a lot more other things, but I'm sure I have run out of my time. My conclusions are, as far as Gaussian optics is concerned, Cartesian sign convention, Petzval curvature, it must be mentioned. And in fact, you could formulate a problem. Okay, the object is below axis by this distance. Calculate the Petzval curvature. Calculate the defocus aberration that you are introducing and ignoring. And it's a very simple problem, but it kind of awakens the mind and not just go just as learning paraxial optics, but not paying any attention about it. And there should be some kind of a flow from Gaussian imaging to diffraction imaging. Usually they are compartmentalized. They are totally separate. You should know. I just learned about imaging. I even learned about distortion and spherical aberration perhaps, but didn't do anything about. And the flow is that yes, Gaussian image is perfect. It's exactly like the object, but in practice, because of the aberrations in the system and diffraction, of course, the image doesn't exactly look like. Now, in everyday life, we take pictures. We don't even think about the quality too much unless the image is blurry. And even that doesn't happen very much today because little cameras like this take very good pictures every day. Of course, we spend $1,000 buying an iPhone or Samsung and so on. So anyway, this is where I will end, and I'll be ready for any simple questions. Thank you very much.
Thank you very much, Vinny. Questions?
So indeed, this is a very good roadmap, starting from simple imaging equation all the way to adaptive optics. As a teacher, as I talk to students in the class, or especially the students having some difficulties understanding some concept, the challenge is they do not see all these things in such a single storyline because it spreads over at least 2 or 3 years in multiple classes, and they all use different terminologies sometimes, different sign conventions, and in different contexts, which is good. But at the same time, it is very difficult to let them connect all these stories. I do my own version in my class as a teacher, but if every faculty or teachers does their own version, it will be a lot of repeat. So can you comment on how at a college we can let students see this overall storyline, not by one effort, but do you have any comments about that?
It's a very good question, and it's a real problem because each and every professor has their own way of dealing with whatever they teach. And my purpose in saying there should be a flow, there should be a continuation, is precisely to break that. And I would think whoever the administrator is, that they bring few of the faculty members who teach this kind of stuff and ask them and tell them, you need to make some kind of a connection. And I'm sure they can get together, have a meeting, and bring some connections. I will do this in my class. I will end my class in this manner. And if you would start from that point, roughly speaking, then move on to whatever that professor wants to teach. My feeling is the person who is teaching geometrical optics, his last lecture should be about diffraction optics, saying this is what you are going to learn next. And the other professor who is going to teach diffraction optics, diffraction imaging, he should first lecture should be on geometrical optics, perfect image, no aberrations, etc. And then go on to the wave theory and the like. That's my, but that doesn't mean it will necessarily happen, but effort could be made. Effort could be made and should be made.
Another question? Now I'll ask you one.
Yes, sir.
So I agree with you that homework is extremely important. Without it, you don't learn very well. As you travel around the world, you visit places where they don't do much homework. Have you convinced them they should be doing homework?
No, they threw me out. I threw out them. Yeah. But two places where I go, I have gone often. One is Taiwan, and the other is Mexico. I have no problem with the homework because first I say I need a teaching assistant because somebody has to grade that homework. And for me to grade the homework is kind of a waste of my time. And my time is very limited because I want to be back home with the grandkids. And so they give me a teaching assistant. I make sure the teaching assistant will also do the homework so that he or she, when is grading the homework, she has done her homework. And of course, typically I would give him or her the solutions so that he doesn't have to struggle. Now sometimes I have gotten good teaching assistants, sometimes not so good. But every time I have made sure it is still done. And other places I just talk like I have here. David will do what he will do and so on. And I'll move on to some other place.
Any other questions?
So,
Yes, sir.
in terms of the paraxial ray tracing, so we have these spreadsheets that students tend to hate because it's an exercise in hand cramping and how accurately they can type into their calculator. So do you think that we've reached a point maybe where we should be providing them with the ray trace, but their job more is to pull out the relevant information from that as opposed to having to go through those calculations?
Yeah, my short answer is, first of all, I do not know how to use computer to do the calculations, to do the plotting and so on. The only thing I have is a calculator like this. And my belief is the moment you use the word spreadsheet, oh, that's already a scary word. Spreadsheet, oh my God. But don't give complex problems that require solutions which may entail a spreadsheet. Give simple problems. You want them to learn the concepts, learn how to solve simple problems, and then go on to using computer for whatever. The moment you give complex problems, more than 2 lenses, it's a complex problem. And doublet, you want to, what kind of information you can get out of a doublet, cancel the aberrations of one lens with that of the other. Those things they should learn so that if and when they want to become designers, they know I have to have more lenses. There are systems which have 30 lenses, for example. You don't want to be finding the principal planes of those and so on using hand calculator. Obviously not. Homework problems in general should be simple and doable and must be done, must be graded. I know of some who gave homework but never graded, never looked at it. That's very bad. Then the professor is not doing his or her job. Also, by the way, these 2 places where I have gone more than 2-3 times, I say, well, whatever I am teaching by my being there, this teaching assistant has to teach in the future. Otherwise, I am wasting my time. And that is happening. That is happening. And I help. I help the instructor with whatever. I can help.
Anything else? Yes.
Share a little bit something about universities in Europe. Now you know we are trying to.
By the way, she is Professor Eva Acosta from Spain, from Santiago. And she works with the professor here. She spends her summers here because it's hot here.
Not only because of that, Professor.
No, in summertime, because it is hot in the summertime.
So now we are trying to unify all Europe with the same, at least subjects or main subjects in every graduate, for every grade. So physics, mathematics, optics. So optics, there is no optics itself, only in a few places. So usually people arrive through physics. So I can speak about what happened with physics. So these last years we have been doing every 10 years or sometimes every 6 years the report of the future, what we are going to teach, what is the important things and all these things. So, and one part, in the first time we did it, one part would say, how, are you going to put some homework? How long you estimate the students need to study every day to learn your subject. So everybody makes the calculations of our homework and everything, and then we put all together and we send to the ministry. You know, we were very happy. It was something sort of individual, and then put everything together. We tried to be unified, a lot of concepts and everything. Well, they went to the ministry, some people study and come back. And then they say, well, we have looked at the numbers and we realize that the students need around 30 hours per day if they really need the time you are saying for the subject, because it's 4 or 5 hours theoretical things a day. Then most of the days they have practice that is 4 hours. It's 9 hours. We are exploiting them, somehow. It's more than a worker time. And then if we put some homework, and everybody wants the best homework, and we were conservative. It was around 1 hour per capita, more or less, in average. So it was they have to spend more than 1 day for doing 1 day. So it's not a defense, but that's why I'm telling you that in Europe sometimes we are relaxing a little bit of homework.
My response to you would be, as I was saying earlier, do not make homework problems hard. Keep them simple so that they are doable, and make them interesting so that students want to work on those problems because they want to learn. Hey, was that object? I said objects are closer than they appear. No, that's the image I'm looking at. And how does it function? Make the problem simple and relate them to everyday life, if possible at all. Harder problems you give the students, even if they do, they'll get disinterested. And of course, trend these days has been for some time, people want to have fun. In my days, we were struggling to learn and get somewhere. But life is what it is. But I'm saying it is the responsibility of the professors, the instructors, to entice the students so that they want to do something. So make the problems relatively simple. Not useless, but relatively simple. Just as I said about the Petzval curvature, cook up a problem. And I have done that. And I'm not very good myself at that because I didn't learn problem solving in my education that I received in India. And I am still scared of problems. I mean it seriously. I have to do it by hand, figure it out. But I do have the mind to make a judgment. Does the solution make sense? And if it makes sense, it may still be right or wrong, but at least I try to do that. As I said, I don't know how to use computers, so I go looking for help. Lots of people know how to run computers, so I can go to lots of people. I pick one and I say, this is what I want done. I have to be smart enough myself to make sure what I get in response makes sense. Because if the person is giving me wrong answer, I'll be using the wrong answer. So, I think make the problem simple. Go ahead.
I just want to add a comment about that. Based on my experience, simple and more insightful question is actually more difficult to answer very often, more engaging. Because when I ask some taking long time kind of questions, many of the students is actually coming up with perfect answer or 80% answer. Although it takes some time, it's a matter of I'm just solving it. But then when I ask very simple but conceptual question, very often many students actually couldn't even find a clue. Like as you said, one lens, one single ray going into it, how does it bend? Even roughly was not easy sometimes. So I agree. I mean, if it's a homework question, it must be simple and insightful in a way that it can tell the important message.
I agree. I agree. I think if your mindset is such that you in fact want the students to learn, you will come up with better problems. If your mindset is such, I'm too busy with my research, I teach it only because I have to, then obviously there would be a problem. I know some professors who are happy to give 20 Bs in a class of 25 and the other 5 barely making A. Or nobody gets an A. It doesn't bother them. It'll bother me a lot. In fact, once I started teaching at the University of Southern California in Los Angeles area. I told the class, nobody will get a grade other than B. But you must make the effort. You may get B minus, and minus sign won't show up on your transcript. But you must make the effort. And I would not give a grade below B. Because I look upon myself, oh, that means I did not do a very good job with the student. And once the students understand, they will come and ask you questions and so on. That's my thinking, at least at this age.
Anything else?
Anybody else?
If not, we'll say thank you, Vinny. Thank you.
And thank you. Thank you all.